Cheng-Yi from Stanford University. Today I'm going to talk about amortized dynamic cell-probe lower bounds from four-party communication. This is a joint work with Omri Weinstein. The cell-probe model proposed by Yao is often used in data structure lower bound results. These lower bounds are robust in the sense that the cell-probe model is a very strong model. All lower bounds proved in it will also hold in, for example, in RAM model and for real computers. In this talk, I'm not going to define formally what the cell-probe model is. It's not crucial. If you don't know it already, that's completely fine. You can just think of it as a RAM model or real computers with appropriate word size. Because the cell-probe model is a very strong model, the highest lower bound proved in it is only log m squared per operation for any data structure by Kasper-Larsen. And moreover, this lower bound assumes the data structure has worst case guarantee for some operations. If we only consider data structures with only amortized time guarantees, then the highest lower bound is only log m per operation by Petrasco and Germain. And here by m, I mean the number of different operations in the data structure problem. For example, if you want to dynamically maintain a graph under edge insertions and deletions, because there are only n squared edges that you can insert or delete, then in this case, m will be at least n squared. And by highest lower bound, I mean you can pick your favorite problem. It can be as hard as you want. Then it has some parameter m. Then in terms of this m, the highest lower bound you can prove is only log m squared. But of course, there are many hard dynamic problems. For example, Amir Aboud and Virginia Vasilevska-Williams showed that under possible assumptions, there are many dynamic problems on graphs that takes linear time or even n squared time per operation. So what I want to say here is that the reason that we cannot prove a high lower bound is not because we don't have good candidates for hard problems. It's because we don't have good techniques for proving high lower bounds. And in this talk, we introduce a new technique which can be used to prove amortized lower bound of log m squared per operation. And moreover, this lower bound will hold even if the data structure only succeed with a very low probability. And I will explain what it means in a few minutes. So before that, first let me define the problem we prove a lower bound for, and Kasper-Larsen did. So the problem is the 2D orthogonal range counting problem. So in this problem, we are going to maintain a set of weighted points in the two-dimensional plane with integer coordinates between 0 and n, and supporting the following two types of operations. The first type is to insert a point at some coordinate with some weight. So here I'm inserting a 9. And second type of operations is to query. Query is the sum of weights of points with coordinates less than some parameters x and y respectively. So by this query, I specify some orthogonal range on this plane, and I just query the sum of weights of points inside this range. So for this query, we get 20 plus 8 plus 9. So the answer to this query should be 37. So this is a very classic problem in computational geometry. And the best known upper bound for it is the range tree. And with update time polylog n, the range tree has query time log n over log n squared. And moreover, this data structure has worst case time guarantees and is deterministic. On the other hand, the highest lower bound known for it with update time polylog n, Kasper-Larsen proved the matching lower bound of log n over log n squared in this case. And his lower bound works if the data structure has worst case update time, and the query time is also worst case, but can be randomized, but the query must be zero error. And in this case, in this paper, we prove the same lower bound, but we extend to the case where the data structure can have an amortized operation time guarantee, and we allow the queries to be wrong for some probability. So more formally, we prove that for this problem, for any problem size n, we can design a hard distribution, sampling from which gives us a sequence of n operations to this problem, orthogonal range counting. And this sequence has n over polylog n updates and n minus n over polylog n queries. Such that for any data structure, if we feed this sequence of operations to this data structure, then the probability that the data structure is too efficient it takes much less than this amount of time, and the data structure is accurate, it answers all queries correctly, this probability is exponentially small. So this is not a standard lower bound statement. I'm not saying anything about its expected running time. I'm not saying anything about its correct probability. I'm just saying that the probability that the data structure is too fast and too accurate is exponentially small. And I will explain what it means and what the implications are in a minute. And moreover, we also our proof technique also can show also works for the case where we're considering the data structure answers 90% of the queries correctly instead of answering all queries correctly. But for simplicity, in the following, let's just assume that let's just consider the case where they answer everything correctly. So before showing you the implications of this theorem, let's first, as a comparison, see what happens if we feed this sequence of operations to the best known upper bound, the range tree. So as I showed in the previous slide, the range tree has update time polylog n. When the range tree has update time polylog n, it has query time log n over log n squared. So if we set this polylog n here to be smaller than the polylog n in this statement, then the total running time of range tree will be n times log n over log n squared. So the point here is that the total running time of the range tree is exactly this expression here. So with the range tree having running time, total running time of n times log n over log n squared, our theorem says that if we want to get any asymptotic improvement, then this data structure must have exponentially low correct probability. So for example, you have some data structure that is always asymptotically faster than range tree, then this first line, the first condition always holds. So the statement of the theorem just becomes that the probability that all answers are correct is exponentially low. So this suggests that this range tree is optimal in a very strong sense. Even if we want any asymptotic improvement, and even if we allow amortization and randomization to get any asymptotic improvement, we must sacrifice a lot of the accuracy. We must only have exponentially low success probability. So on the other hand, if we only consider the data structures that are always correct, this theorem tells us some information about where the hardness comes from, how this problem is hard. So if we plug in a data structure that is always correct, then this condition always holds. Then statement becomes that the probability that the data structure is asymptotically faster than the range tree is exponentially small over the randomness of the input. So for some problems, the problem is hard on some input distribution, maybe because with constant probability, there are hard inputs for this data structure, probably different constant fraction for different data structures. Then when we are unlucky and get those inputs, then we will spend a lot of time. So the expected running time is high for those problems. But this is not the case for this problem. We know that for this problem, from the statement, we know that the data structure almost always takes n times log n over log n squared time. So we cannot even design any heuristics for this problem. We cannot design data structure that is slow in worst case or on average, but fast in some cases. So no matter how you design the data structure, as long as it's always correct, then with except for exponentially small probability, it will always take n times log n over log n squared time, matches the time bound of the range tree. Also, there's one more corollary of our theorem, that if we have a data structure with expected time alpha factor of the performance of the range tree, then by application of Markov's inequality and union bound, and together with our theorem, then we imply that this data structure, the probability that this data structure answers all queries correctly is at most alpha. And this boundary is also tight, because one thing we could always do is to first flip a random coin, and with probability alpha, we just run range tree in the following before the first query. And with probability 1 minus alpha, we just do nothing. We output 0 for all of the following queries. And for this simple data structure, of course, the expected running time is alpha times the performance of the run tree, and with the probability alpha, we answer all queries correctly. So this statement is also tight. So in the remaining time, I will briefly introduce or describe some ideas in our proof techniques. Okay, so we want to prove some data structure lower bound, assuming we have a hard input, hard distribution for the operation of sequences. So first, we apply a standard argument. So first, let's consider a sequence of operations drawn from this hard input distribution. Let's assume this is the sequence, and U indicates updates, and Q indicates the queries. So we fix two consecutive intervals in this sequence, the red interval here and the blue interval after that. So we fix the data structure and consider how it runs when we feed this sequence into it. So during this first red interval, the data structure may access some of the memory cells. Let's say it accesses these red memory cells. And then if we continue simulating it, then during the blue interval, it may access a possibly different subset of memory cells. Let's say there are these blue memory cells. And of course, it's completely possible that there are some of the memory cells that are accessed by the data structure during both of the intervals. So let's color them black in this case. So the standard argument shows that it suffices to lower bound the expected number of black cells for different interval pairs. So if we can prove a lower bound on this number of black cells for every interval pair, then by summing up these lower bounds in the right way and do the counting argument, we can get a lower bound on the number of memory accesses the data structure does on this sequence of operations in the entire procedure. And this lower bound will be a time lower bound. So everything boils down to to prove a lower bound for this expected number of black cells for different interval pairs. And in order to prove this, the first observation is that these black cells are the only way to convey information from the updates in the first interval to queries in the second interval. So in order to answer these blue queries, the data structure must learn something about what has happened in the past. And this includes the updates in this red interval. And in some sense, these black cells are the only way to pass these red updates to pass information to the future. And in this case, the following communication game is usually used as a proxy. So consider this following communication game. So we still have a sequence of operations, and we have two intervals in it, the red interval and the blue interval, and we get two players, Alice and Bob. So we give the first sequence of operations to Alice, and give the second sequence of the operations to Bob. And for all operations outside these two intervals, we make them public, so both of the players can see them. So after these two players receive their inputs, they start to communicate by sending messages back and forth, and eventually they need to answer all queries in the second interval, all the blue queries. And their goal is to minimize the number of bits transmitted during this process. So the proof of data structure lower bound usually goes in two steps. First, we try to show that the complexity of this communication game is related to the performance of the data structure. So intuitively, if the data structure proposes very few cells in common during these two intervals, then it means there's very little interaction between the red updates and the blue queries. And this will result in a low communication cost. So for example, in an extreme case where the data structure never proposes the same cell during these two intervals, then in this case, Bob knows that the data structure during the blue interval, every memory cell it accesses, its value was never changed during this red interval. So he might as well just throw away all the operations during the red interval and just simulate the data structure on all the operations here, then jump directly to the blue interval and continue the simulation. And in this case, with no communication at all, Bob can just answer all the queries on his own. So first, we try to show this complexity of the of the communication game is related to the performance of the data structure, then because this is a well-defined communication game, which we have a relatively good understanding, so we can just prove a communication lower bound for it. Then combining these two parts, we can get a lower bound on the number of black cells, which will give us a data structure lower bound. But here, also one thing I haven't mentioned is that the communication model is actually very important in this case. So the version I just described to you is in the most standard deterministic communication model. For example, we can add more restrictions to what the players are allowed to do. Intuitively, by adding more restrictions, it will be easier for us to do the second step because it's easier to prove a communication lower bound. But on the other hand, if the model is too restrictive, then even if we have the same data structure, we might have a higher communication cost. Makes us harder to do the first step. For a similar reason, we can also add more power to the data structure to the communication model. Say, for example, by allowing the players to use randomness or non-determinism. But in this case, if the model is too powerful, then it might be harder to prove a communication lower bound, or even impossible to prove the lower bound we want. But with the same data structure, we might be able to get a faster simulation. We might be able to get a faster communication protocol. So the key point here is to find the most suitable model for the data structure problem you want to prove a lower bound for. So previously, there are some work in this framework that studies the deterministic model and the non-deterministic model by Petrasco and Torup. And earlier this year, a non-deterministic model with more restrictions was studied. And in this paper, we proposed a new communication model, which for our problem, the 2D orthogonal range counting, performs strictly better than all these previous three models. So here, I will briefly describe this four-party communication model. So besides the two players, Alice and Bob, who knows the parts of the input X and Y respectively, we have two extra players, Merlin and Megan. So in this model, in the protocol first, Merlin looks at his input pair X and Y and sends to Bob some short advice. So unlike most of the prover and verifier model, here Merlin's message doesn't need to be verified. The players can just trust whatever Merlin says. So for example, one thing Merlin could always do is to look at his input pair and compute the function value on his own, and then just tells Bob what the function value is, and then they are done. But in our setting, that the function output takes a long string to describe. So in this case, the message sent from Merlin will be very long, and the message length from Merlin is one parameter in our communication cost. So this protocol might have a higher communication cost. After Merlin sends his first message, Megan looks at the input pair and plays the role of the prover in this case. She looks at the input pair and sends some claim about it to the players. And then the players start to communicate as if they were in the standard communication model. So their first task is to verify whether Megan's claim about this input pair is correct or not. Then if this claim is correct, then they can use this information, and then their goal is to compute this function value. So this completes the procedure of the protocol, and the communication cost of the protocol is defined to be the tuple of number of bits sent by each player. So it's not hard to believe that because of this powerful trusted Merlin, there are many things that you could not do in the other models with low communication costs you can do in this model. And also, on the other hand, we prove that this doesn't increase the difficulty of proving communication lower bound by too much. So one general approach for proving communication lower bound is to first show if we have an efficient protocol, then there's a large monochromatic rectangle. And in this case, for this model, we actually prove that if there's an efficient protocol, then there's a large rectangle in which there's one color that appears there's one color appears more often than expected. So there's a large rectangle with significant bias in its colors. And for our problem, compared to the previous models, we obtain a strictly more efficient protocol from the same data structure because we have this powerful trusted Merlin, and we are able to prove the same communication lower bound. And combining these two facts together, we prove a strictly higher data structure lower bound. And in conclusion, we prove the amortized lower bound for data structure with tiny success probability. And also, besides that, we show some connection to the static data structure that if we can improve so we prove some exponentially low probability. If we can improve our theorem by prove it for even smaller probability, then it will imply a new static data structure lower bound. But it seems that improving this theorem requires new ideas. And we have a session in our paper discussing this issue. And there's a related open problem that whether we can still prove a log n squared lower bound if the query output has only one bit. For example, whether we can still prove log n lower bound for range counting modulo 2. Thank you.
Questions? Go ahead.
Yes, because here we restrict Merlin to send a very short advice to prevent the trivial protocol for Merlin just send the output. So this message length should be very small, but Megan can send a very long message. Yeah, Megan's message length is actually unlimited in this case, but the players need to verify that. Yeah, briefly, Merlin's message in this case will be the relative. So you look at all the cells that are probed by this data structure in this blue interval, and and Merlin's message corresponds to the subset in this set where these black cells are. So maybe the 17th cell I probed during this blue interval is the black cell, and maybe 27th is. So this relative order, in this sorted order of probing cells, which ones are but not counted. And in Megan's message, she provides the actual addresses and content.
Any questions? Let's thank Hao Chen and all the other speakers of the session.